Hello, chemistry friends. So we had a snow day this week, so we get to do another video episode for chemistry. So I'm sure you've all read your syllabus and you are aware that we are switching all the way back now to chapter 2. Chapter 2, we are now on page, 37 of your book. So going back to chapter 2. So now, if you like this chapter, then physics is for you. So the reason we didn't do this chapter until now is because it's pretty math heavy. Hopefully your math has gotten a little better since September, and maybe some of you even know how to do some of the things in this chapter already. So basically we're going to be talking about energy now. So energy is the ability to do work. So you eat food for some energy in your body, and work is what happens when something moves. So I can push against this wall all day long, but I will have done no work unless I can get the wall to move. And I hope I don't get my wall to move today. So just so you need to know about energy and work. You might want to know the difference between potential and kinetic energy. Potential is energy that's stored. So food has potential energy. There's energy stored in there. Kinetic energy is energy in motion. So if you'll do again more of this in physics, but if you have, we have a water balloon launcher and you have two guys holding it and someone pulls back on the strings, that's storing the energy in there. That's potential energy. And then when you let that balloon go and it shoots across the yard, that's kinetic energy. That's energy of motion. So you may want to know the difference between those things. So the first thing we need to do is talk about the difference in temperature. So in our country, we measure temperature in Fahrenheit, which we use a capital F. Hopefully this marker works. F and degrees Fahrenheit, actually. But most other places in the world measure energy in Celsius. So they have degrees C for Celsius. They're both capital letters. And you're going to need to know how to convert between them. The problem is, if you are not super good with math, you're going to have a problem if you don't follow the order of operations. Sometimes you get the formula set up correctly, but if you don't do it in the right order, your math will not work. So you need to know that degrees Celsius equals 5/9 times, there's a parentheses, your degrees Fahrenheit minus 32 degrees. So it's very important that you work inside the parentheses first, and then multiply by your 5, and then divide by 9. If you don't subtract this first and you try to multiply and divide first, it's not going to work. So you need to work inside the parentheses first. So you take your temperature in Fahrenheit, like today is a whole 17 degrees, I think, or dropping. Maybe it's 13 now. I don't know, it's freezing. And less than freezing. And then you subtract 32, and then you would multiply by 5, divide by 9, and you'll get your temperature in Celsius. If you have the opposite, you have your temperature in Celsius, and you want to change to Fahrenheit, you're going to want to do exactly the opposite. Then you're going to want to multiply by 9 and divide by 5 your degrees Celsius. So you do that first, and then once you multiply by 9, divide by 5, this is flipped, then you're going to want to add your 32 degrees. Order of operations, very important. So make sure you, memorize. I would say you'd have to memorize them. But make sure if you have Fahrenheit, you subtract 32 first, then multiply by 5, divide by 9. If you have Celsius, you're going to want to multiply by 9, divide by 5, and then add 32. Very careful. Okay, so we are not going to do this lab, which is on page 43. It's calibrating your thermometer. So we've been using thermometers in our lab. what you would have learned from this lab is two things. One, your thermometer is not that great. So the whole reason that most of the world uses Celsius is because water boils at 100 degrees Celsius and it freezes at 0 degrees Celsius. So those are things you're going to need to remember. So if you see on page 44, I'm not going to draw it, there's this little chart where we were supposed to put some ice water into a beaker and then take the temperature as the water is heating up. But as long as there's still ice in that water, your temperature should have been it really should have been at 0. If you had a perfect thermometer, your thermometer, as long as there's ice in that water is at a constant temperature of 0 as long as there's ice in there. And so that should have been at 0, 0, 0, 0, but yours wouldn't have been. Some of them are at +2, some of them are at +4, but none of them are great. And then your water starts to boil, it starts to get very warm until it boils, and then it should have also tapered off, should have got warmer, 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 and then tapered off right at 100. So at 100 degrees, your water should have boiled. And once it's boiling, it doesn't get any hotter than 100 degrees. Water boils at 100 and it stays at 100. It might evaporate, but it stays at 100. So when it's freezing, it's at 0 degrees C, and when it's boiling, it's at 100 degrees C, and it'll be constant at those temperatures. So you would have learned from your lab that when your thermometer's not that great, it might be a couple degrees off, but none of our other labs are very, need to be that carefully measured, so it's not a huge deal. But then just make sure, I'm backing up to page 42 now, that if ice and water are thoroughly mixed, your temperature will stay the same, it's constant temperature, and it'll be at 0 degrees C or 32 degrees Fahrenheit. Similarly, water boils at 100 degrees C, which works out, if you put it into these formulas, to be 212 degrees F. Okay, so these are obviously easier to remember here, degrees Celsius, but these are the ones we typically use in America. So today is a lot lower than 32 degrees, so obviously there's lots of ice outside today. And I don't know that I've ever want to be anywhere that it's going to be 212 degrees Fahrenheit, so that's too hot for me. Okay, so you can skip this lab this week. It's a long lab, and the math in this chapter is going to be something that you're going to want to focus on anyways. Okay, so make sure you know the temperature that water boils and freezes. Now we're going to put these two formulas into practice. Page 45, example 2.1. A student uses a Fahrenheit thermometer to do a chemistry experiment, but then must convert his or her answer to Celsius. The temperature reading was 50 degrees Fahrenheit. What's the temperature in Celsius? So you have Fahrenheit, and you want to convert to Celsius. So the first thing you're going to do is do 50.0 minus 32. Keep in mind this is only 2 significant digits, but you're going to want to do that first. And then you're going to want to multiply by 5 and divide by 9. So work inside the parentheses first, then multiply, then divide. And that will give you 10.0 degrees Celsius. This is exact number, so you can, the significant digits are going to be based on this. Exact numbers, so just, if you have 3 significant digits here, you'll have 3 significant digits in your answer, just so you know. Okay. Next one. We usually say that room temperature is 25 degrees C. What is that temperature in Fahrenheit? So if you know your degrees C, you're going to say 25 25 degrees C, you're going to first multiply by 9, divide by 5, and then add 32. Make sure you do these in your calculator so that you get the order of operations correctly. So if you multiply by 9 first, divide by 5, and then add 32, your degrees Fahrenheit is going to be 77 degrees. Okay? So 25 degrees Celsius is about 77 degrees. I guess I have a degree there. Okay. So make sure that you can go back and forwards. Celsius to Fahrenheit, Fahrenheit to Celsius. Make sure that you get these order of operations correctly. Okay, so when we're talking about next week, we're going to be doing calorimetry. And again, this is pretty math heavy. There's certain scenarios that I cannot have negative numbers. So the whole reason, well, without showing you the problems, it's hard to explain why you can't have negative numbers, but you're going to be divided by negative numbers. We don't want to have I and worry about all that. So we're going to learn a formula. It's a temperature. It's called the Kelvin scale. It's made with a big capital K. And Kelvin is where the lowest temperature ever possible is still a positive number. So it's your degrees Celsius, and then you add 273.15 degrees. So that means at negative 273.15, there's still some movement of atoms. So if you add 273.15, you're guaranteed to never have a negative number. So the whole purpose of the Kelvin scale is to not get negative numbers in your temperature. Okay? So let's do, this is page 47, example 2.2. What's the boiling temperature of water in Kelvin? Well, the boiling temperature of water in Celsius is 100. So 100 degrees plus 273.15, hopefully you can do that math, should be 373.15 degrees Kelvin. So I just write 373.15 K for Kelvin. Okay, so this one actually, it says that it's 0.0, so I would have to round that to 0.2 so that I have the same significant digits. Okay, so 373.2 kelvins. The lowest temperature that has ever been recorded in the U.S. is negative 80 degrees F. Ooh. Okay, so negative 80.0 degrees Fahrenheit. What is that temperature in Kelvin? Well, first, if it's in Fahrenheit, I'm going to have to convert to Celsius. So I'm going to have to add my, subtract 32 first, and then I'm going to have to multiply by 5 and divide by 9, and that's going to give me negative 62.2 degrees C. Ooh, brr, that's cold. I'm guessing that's in Alaska somewhere. All right, then we're going to have to convert that to Kelvin. So then we're going to add 273.15 to that. Remember, when we're adding, subtracting significant digits, I round to my least significant place, which is going to be this place. So I'm going to be 210. It's 9.5, but then it rounds. If this is 9.5, it's going to round this up to a 0, which rounds this up to a 1. So the coldest temperature ever in America is still 211.0 K. So sounds balmy, but it's not. It's very cold. Okay, so even very, very, very cold temperatures are big numbers in the Kelvin scale. Okay, so the majority of our math is going to be done next week. We're going to do a kind of a fun lab with a little piece of metal and a little bit of physics thrown in there. Okay, but something else that you might want to remember is we measure energy in calories and joules. We measure it in both ways. So 1 calorie, small c, is the same as 4.184 joules. So this is another reason why we didn't throw this chapter in there in week 3, because this isn't really, one, it's not really chemistry, and 2, you're learning all these different things that don't have anything to do with chemistry really. So this is really, you'll use joules a lot when you're in physics. And 1 calorie is the same as 4.184 joules. A calorie is the amount of heat necessary to warm 1 gram of water, so a teeny tiny little square of water, right? If you have a cubic square of water, warm that much water 1 degree Celsius. So if I take the amount of energy to heat 1 gram of water 1 degree Celsius, that's 1 calorie, or 4.184 joules. Okay? Now we use calories in our English language, but the problem is they're not the same calories. So the calories that I eat when I'm eating my Snickers bar or my Valentine's Day candy is going to be 1 capital C-A-L calorie, and that is so this is 1 food calorie that I'm eating, and that's actually 1,000 chemistry calories. So a small c for chemistry calorie, there's 1,000 of them, and 1 of the calories that I eat in my food. So just so you know, you might want to know that conversion, that when we're measuring calories in chemistry or joules, it's not the same calories that are in the food that you eat, even though you talk about calories all the time. So, all right, that is all that we're going to cover in this lesson. I would just encourage you, especially if you are not super good with math, get your calculators out, work through these problems so you get your order of operations correct. Okay? Stay warm, and we'll talk about specific heat and some fun calorimetry things next week in class. See you soon. Bye.